Hello everybody, we are on to experiment 11, and this is where things definitely look like the book is starting to get a little bit more complex. I'm actually going to be splitting this experiment 11 into probably a number of parts because changes have to occur along the way on the circuit. So I don't want to make an hour-long video. I will instead do these in chunks. So this circuit is supposed to represent, the title is called slow speed oscillation, and the idea behind it is this LED is supposed to kind of flash every so often. And we've done something like this before because if you guys remember, we had that latching relay experiment. I think it was maybe on, I don't know, 7 or 8 or something like that, where, you know, when the coil had current flowing through it, it would move the latch, which would then turn the power supply off to the relay, which would then, you know, it would kind of do this loop where it would end up flickering the light on and off, but we would hear the clicking of the relay. We are able to do similar things with transistors. In this case, we are using a special kind that's called a programmable unijunction transistor, also referred to with the acronym PUT. So we will be using this PUT in the center of our circuit. And one thing you'll notice, if you recall the use of the transistors that you know, we had oriented on this board in previous experiments, they were actually facing the other direction. In fact, let me grab, see if this works for my viewers. I've got a little hand magnifying glass here, and just to kind of blow that up a little bit. So this guy is pointed that way. So anyways, gotta make sure I don't focus light on that. Yeah, so as you can see, pointing the opposite direction. Anyways, bearing that in mind, he, just like the other transistor we used, which was the, I think it was the 2N2222, this guy has 3 pins just like the other transistor. However, they are called different names. So rather than a collector with a base pin and an emitter, we have an anode pin, which is like the inbound, a gate pin, and a cathode pin. So, and the anode and the cathode are kind of more akin to the, you know, ends of a battery, the anode and the cathode. So, the idea behind the PUT is that we have that gate pin, which is a little bit of like, so if we think back to the regular transistor that we used, the idea behind that guy was, hey, depending on how much voltage is being sent to the base pin, that would be amplified, or that would amplify the let me rephrase that. Depending on how much voltage was being sent to the base pin, it was amplifying that on the output emitter pin, using the collector pin as the source of the current. So this guy's a little different because the gate pin is actually a threshold for when the door opens between the anode and the cathode. So it's basically saying until a particular voltage buildup is pushing on the door of the anode, it won't be let through until it meets or exceeds that is on the gate pin. It's kind of a, I don't know if I verbally said that the best way, but so just to reiterate, I'll use an example of, hey, if we have 5 volts pushing against our gate pin, until we have at least 5 volts pushing against the anode pin, nothing will happen. But once we have that much or more pushing against the anode pin so that it meets or exceeds the gate pin voltage, it's allowed to flow through and out the cathode pin. So, bearing that in mind, with this setup, we have See if this will help. So we basically have a we've got a line from the well, let's just start at the resistor. So if we were to look right here, we've got a resistor that is basically running from the power to this common strip, and then grab a pointer of some kind here. Pen will work. So we've got the resistor running from the power to this common strip, and the capacitor is forking off of this, or we'll say paralleling off of it, and returning back to ground. So we have a kind of a miniature circuit right here going on, and this is charging the capacitor, right? So this, remember, current doesn't flow through capacitors. It's just building up a charge of electrons on one of the plates of the capacitor. Okay. Likewise, we have a circuit that goes from the same point through here, and this line is running to our anode, the equivalent of the collector pin of our other type of transistor. And right here we have a resistor directly connected between our power source and the gate pin. So whatever voltage is left after dropping, so the voltage starts out at, like, I think in our case, and we'll check this, I think it's about 13.5 volts, even though the supply is rated at 12. It will have a certain amount of voltage drop here, and whatever is left will be the threshold for this put. So what happens is the capacitor will constantly be pushing, whatever the voltage charge is against the anode of this put. But until that charge is built up enough so that it reaches or exceeds that threshold to the gate pin, nothing will happen. Once it does, and it'll discharge itself through the anode, through the cathode, and it will light up the LED. So what we end up with is an oscillator that flashes this light. So I'll turn this one on. Oh, and keep in mind, this is a 2.2 microfarad capacitor, so relatively small, not much charge time there. So it's going to flash pretty quickly. So as you see, that's pretty fast. That's like, 1 a second or so. So what we're going to try, because this is all happening so fast, and what the book recommended was, hey, let's, take the capacitor out, throw one in there that takes a little bit longer to charge, so that we have time to take measurements. So let me take the capacitor out for a sec and just discharge him across one of these guys, just to be sure. And so this guy is a 22 microfarad, so he's 10 times larger than the other capacitor. So I'm going to put him in play, and we will retry this experiment. And once we get it up and going and confirm that it's working, we will then take some measurements. So, turn it back on. And so far nothing. But keep in mind, it's going to take a little longer for that capacitor to charge. In fact, it should take about 10 times longer. So there was a flash. So it's probably like, 10 to 12 seconds. But yeah, there we go. So we have a slower oscillator than what we had before. And what we can do to check what that threshold is, like let's start there, because we know that here I'll put my leads on our power source first, just to get a baseline of what the voltages we're working on. So we've got 13.6 volts coming into this circuit. And let's check, since we know that the resistor right here is coming straight from power, and we know that after this resistor we're going straight into the gate pin. Let's just check the voltage drop across this resistor. If I can actually hold it steady. So it's 4.8 volts of voltage drop. Right? 4.8, and we said that this was 13.5. So 4.8 from 13.5 minus 4.8. So that's giving us about 8.7 volts that is being set as the threshold on the gate pin. So that means that in theory, our capacitor here, if I were to take a live reading of what the charge is, let me see if I can do this without getting in the way of the camera, we should be discharging at about that threshold. So you see how it's charging up? Boom. So it dropped it all. I notice my, here we'll watch it a couple more times. Boom. So yeah, it drops it just after it exceeds the threshold. So I noticed that while the capacitor climbs there, you see my multimeter seems to, like, just for a flicker of a second, it loses its, watch, right about here. It's interesting that whatever internal stuff is going on with the charging of that capacitor, the building up of that tension, that imbalance of the electrons between the plates, for some reason it, at a specific point, is very difficult for the multimeter to track, just briefly, and then it comes back on. Nevertheless, you can see it's consistently discharging at that threshold amount. So it's pretty cool. So if we have a smaller capacitor, I guess the rule is, hey, if there's less work to be done to charge to that voltage amount, then that creates a faster oscillation. If we reach that charge, that voltage threshold that the gate needs faster, then we're able to oscillate faster. So this can be an interesting tool for us for all kinds of things related to oscillation. In fact, when I first started out, I was puzzled because we have super useful tools such as oscilloscopes and things of that nature that are built to examine oscillating waveforms. And being a newbie to electronic work, I questioned in what circumstances would I start to see oscillations. And once you start involving capacitors with puts or things of that nature where there's thresholds to meet before discharges occur, this is definitely where you start to see waveforms come into play. So I can definitely see a purchase in my future eventually of an oscilloscope, but those are definitely expensive. So anyways, I will be moving on to part 2 of this experiment 11 in the next video, so stay tuned.